Hello, everyone. Let's discuss another Leetcode problem today. And this is a blind 75 list problem. And this is a hard problem, but we'll actually figure it out. So today's problem is problem 42, trapping rainwater. So the description says we are given n non-negative integers, and each of these represent the elevation map where the width of each bar is 1. So basically each number in the array represents the width of a rectangular bar where the height of the rectangular bar where the width is 1. We have to compute how much water it can trap after raining. Okay, so as you can see in the first example, you see here this is the input. So each of these values actually represent the height. As you can see, the height is 0 here, right? And then the height is 1 here, the next height is like 0 again, right? Next height is 2. Okay, so now the rectangular bars are actually drawn, and you can see like each of them has a width of 1, right? So this is width of 1, this is 1, this is 1, this is 1, right? Okay, and if I actually draw them like this, and then we actually color code them, you can easily see this blue color is actually the water, right? So how much amount of water it can store is 1 here, 1 here, 2 here, 1 here, 1 here. So overall 6. Okay, so how do we solve this problem? I have drawn the problem 1 here. Let's talk about the most obvious approach to solve this problem. So let's say we want to see how much water actually is stored here, right? So you see the height here is 0. And as you can see, obviously we can store some water here, but uh, obviously we can store some water here, but how much water, it depends on two things. First thing is how tall a wall we have in the right side of the slot and how tall we have a wall on the left side of the slot, because those walls are going to determine the water level, right? So if you see on the right side, this is the wall with the highest height, right? On the left side, you can see this is the wall with the highest height, or this is the tallest wall, right? So these two walls are actually going to define the water level. And if I say like the left max and right max, let's say this is the left max and the right max, the water level is actually equal to the smaller of these two walls, right? Okay, so water level is that. And as you can see, the left max is here, its left max is 2 and the right max is 3, right? So the minimum of left max and right max is 2. So water level actually depends on this. So water level is going to be 2, and the height here is 0. So 2 minus 0 equals to 2. So 2 units of water actually can be stored in these index, right? So that's simple. So how much time like it will take to determine this? So as you can see, for these index, how much water we need to have, we have to go through all of these to find out the maximum or the tallest rectangle, and then we also have to go through all of these to find the maximum or the tallest rectangle here, right? So in total, like it's like we have to go like n minus 1 places. We have to check n minus 1, right? So it's, you can say for each location we need order of n checkings to find the left max, and the right max, right? Okay, and so we have to do this for every index, right? For every index we have to find the left max, the right max. So in total there are like n of them, so it's order of n squared. So in order of n squared time, we are going to determine how much water can be stored in each index. Okay, so that's pretty simple and intuitive, and we found an algorithm with a time complexity of order of n squared. And you see this doesn't use any extra space. Okay, so as you can see, for this location we actually read all of these and then all of these, right? Then similarly for the next location, we will be reading, like trying to find the tallest in the right side and tallest in the left side. So we are actually doing this reading again and again. So why don't we just do some pre-processing and read one time to get the left max and the right max, right? So if we have two arrays, say left max array and right max array, and if we just store the values here, so I have two arrays and I do a pre-processing. At the beginning, I do a calculation. So here you see there is no left max, so there is nothing here, right? So the first value is going to be 0. And then this one is like the maximum is 0. This one is a height of 1. So the maximum to this index, the left, what is the maximum here is 1, right? Okay, so it's 1 here, and then maximum among this is 2 here. Okay, so 2, 2, 2. Now this one you see is 3, but it's still the left to it is 2. But now for this location, the highest, the tallest wall in the left is 3, then 3, 3, 3, right? Okay. Similarly, for the right max, yeah, there is nothing here. So at the beginning, we'll have like 0. So this is the 0. And then right of these, what is the highest, tallest wall or tallest rectangle? It's 1. And then we have 2, right? For these location, we have 2. Even for this location, we have 2. Then for this one, we have 3. Then 3, 3, 3, 3, 3, 3. Okay. Now we have the left max, and the right max values. Now for any location, so how much time it took to calculate this is order of n. How much time it took to calculate this is order of n. Now, say for this location, I want to find out how much water I can store, right? So what I do is I just take the maximum of these two, sorry, minimum of these two, because the water level is going to be decided by the minimum. So not this one, this is going to be decided by this. So 2 minus the height of this level, which is 0, right? Okay, 2 minus 0 equals to 2. So that means for this location, I am going to add 2, right? Okay. Similarly, say I want to have like how much water I can get in this location, right? So I take the minimum of 1 and 3. So 1, and the height is 0. So 1 minus 0 is 1, right? So that means for this location, I'm going to store 1 unit of water. Okay, so it sounds very pretty simple. We have to do this calculation, for each of the indices, right? So in total, there are like n indices. So the time complexity is going to be n, and this calculation, like this comparison, can be done in constant time. So order of 1. So for n indices, it's order of n. Okay. The other thing is there is now some space complexity associated. So you see if this one takes some space, the result of the pre-processed array, right? So the space complexity also becomes order of n. Okay. So now we have a better algorithm, order of n, but we have a space complexity of order of n. Now let's think, can we do even better? Now this part is a little bit tricky, but I guess like if we do a dry run, it will be more easier to you. Okay, so here is the trick here. Actually, we don't need to look for both the left max and the right max. Not like that. Let me explain this. So let's have 2 pointers. One is left and one right. So the left pointer is going to be moving in this direction, and the right pointer is going to move on the other direction, right? Okay. And as we know, the amount of water in each location depends on the highest wall on the left side and the highest wall on the right side. So let's say initially my left max is going to be here, pointing here, and the right max is going to be pointing here, right? Okay. And then we have 2 pointers. Let's remove this because we are going to do it on the run. And sorry. So let's have the left pointer. So this is the left pointer and this is the right pointer. Okay. So the left pointer will be moving in this direction and the right pointer is going to move in this direction. And in the run, along with the run, I am going to calculate the amount of stored water. Okay, so let's say this. So if the height of the rectangle of the left max at certain point is less than the height of the rectangle on the left pointer, right? In that case, so let's say this is the condition 1. In that case, what do? I update the left max, obviously, right? So because that is the even higher wall, I got a higher wall at this index. So left max is going to be updated, right? Similarly, if I see that the height at the right max is less than at the height of the right, okay? So in that case, right max is going to be updated. Okay, that's pretty simple. So as you can see here, initially the left is here, the left value is 1 and the left max value is 0. So obviously what's going to happen is the left max is going to be updated and pointed here, right? And the left will move here. Okay, similarly you can see the right value is 2 and the right max is 1. So the right max is obviously going to be updated to this. And the right is going to be here. Okay. Now the left is here and the left is here and the right is here. Now what? You see that none of these two conditions are not getting satisfied, right? Because both the right is smaller than the right max, the left is smaller than the left max. So what does it mean? It means that we are actually both of the left and the right pointers are actually pointing some pit. It's not pointing to any wall. So wall is not getting updated. So there comes the third condition. So the third condition says we will check now how much water actually is going to be stored here or here. That one depends on the left max and the right max. But the thing is, very carefully notice this, actually it depends on one of them, not both of them. Here is the thing, if the height of, so this is not fulfilled, this is not fulfilled. Now the third condition, if the left max is less than the height of the right max, in that case, in the result, I am going to add height of left max minus height of left. So you see the left max is now 1 and the left height at the left is, so let's say height of the left max is 1 and height of the left is 0, right? So here 1 minus 0 is 1. So the result, what I'm going to do is I'm going to add 1 to the result. That means add 1 unit to the result. Now you can ask me why I am just considering the left max, why I'm not considering the right max. This is the reason. Let's see. So I'm trying to find out how much water is going to be here, right? Now this water, you see, for sure I can say that this is my highest left wall. For sure I can say that, right? But I cannot say if this is my highest right wall. I cannot say that. Can I say that? I cannot say that. The reason is, you see, there are two options. Say this is the right max, right? Now you can say, hey, you see, you even have a bigger wall here, right? You don't know what is the height of the walls are here, right? See, you have a taller wall here, but it doesn't matter. You see that even if I have a taller wall here, the amount of water here actually is limited by these left max. That's clear, right? Or in the other case, what would have happened is, let's say this, we had like a shorter wall. So this is already, so say right max was already like this. Let's say this is the other case. Right max was already like this. And so, and there was no other wall here that is actually taller than right max. Even in that case, you see that the water level here, the water level is actually determined only by the left max. You see, the water level is determined by the left max, not by the right max. So in both cases, the left max actually determines how much, what is the water level is going to be the. So that's why I subtract the left height from the left max size. And the other issue is like, okay, so I'm done. So I'm adding 1 here. And the left max is still is here. And I'm adding 1 and I am moving my pointer here, right? Okay. So I'm moving my pointer here. And right max is still here. And the right is here. Okay, next you see this condition fulfills. So my left max is now going to be assigned here, right? Okay. So the left moves here. Okay. Okay. Next, you see, let's talk about this. If left max, say, greater than equal to height of right max, in that case, in the result, I'm going to add the height of right max, this time right max, minus height of right. The same logic plays here. So you see, the right knows that for sure this is going to be the tallest wall to the right of it. But what it doesn't know is how much, what is the tallest wall on the left, right? It doesn't know that, but it actually doesn't need to know this. Even if there is a taller wall on the left, still the water is going to be determined by the right max, okay? Or if this was already taller and there was nothing, even in that case, the water was going to be determined. So if left max was even taller, even in that case, the water was going to be determined by the right max. Okay. So in this case, I just care about the right max minus height of the right. So it's like 2 minus 1 equals to 1. That means I am going to add 1 here, right? So 1 unit of water here. So I'll keep on doing this in both directions. So there are like 4 things, 4 conditions I'm going to check. And this is the trickiest part, why I just consider the left max, and when I consider only the left max, and when I consider only the right max. Okay, so you see both of these pointers are actually moving. So how much time it's taking is order of n, right? And I will keep on moving this until the left pointer and the right pointer don't cross each other. Okay, so it's order of n. And as you can see, so the time complexity is order of n, and space, well, I didn't use any extra space. So it's order of 1. Okay, so this is a little bit tricky algorithm, but I hope I actually explained to you. Okay, so let's take a look at the code. The left max is set to the left position, the first position, and let's take a look at the code. The left max is set to the first position, and the right max is set to the last position. The left is set to the second position, and the right is set to the second last position. And this is the result, like where we add up all the units of water. So we'll keep on doing this until the left pointer crosses the right pointer, and then we exercise the 4 conditions that we explained. We'll first check if the height at left is greater than equals to height of the left max. In that case, we will update the left max index and move the left by 1. Similarly, if the height of the right is greater than equal to the height of the right max, then we update the right max and move the right one place to the left. And otherwise, if the height of the left max is greater than equals to height of the right max, in that case, we'll subtract the height of the right from the height of the right max and add it to the result and move the right pointer. Or if it's the opposite, that means height of the left max is greater than the height of the right max. In that case, we will just subtract the height of the left from height of the left max, add that to the result, and move the left pointer to the right. And finally, everything is going to be added to the result, and we return the result, that is the units of water that are trapped. So that's it, and thanks for watching. And as you can see, this is pretty fast. This is order of n algorithm with order of like constant space. And thanks for everyone for watching. We'll come back with another problem next time.